Hello, Algebra 1. Here is a video of the Unit 9 test review. This entire review is comprised of exponential growth or exponential decay. I'm going to go through each section, maybe do quite a few of a lot of these because they're pretty similar and try to point out a few things. At the very end of the review, see there's word problems on the next page. At the very end of the review, there's a section called Spiral Review. This time I'm going to do my best to go back. So notice we have some quadratics. We have, mostly quadratics, factoring, what do you do with a parabola, and how do you solve some basic linear equations. But to begin with, we have exponential functions. This is what we've been learning. First, we have to be able to tell whether or not something is an exponential function. It only has to have one thing that is true. X needs to be in the exponent spot. If it's not in the exponent spot, it's not exponential. So an example would be 2 to the x. X is the exponent, it's exponential. B to the x, it's exponential. 2x, or not 2x, 2 plus 3.5 divided by 2. And this whole thing is raised to the power of x. X is in the exponent spot, it's exponential. Something that is not exponential would be something like x squared. It has an exponent, but it's not x. So this would not be exponential. So once we get that out of the way, we know that all exponentials have x in the x spot, and they are all in standard form as y equals some value a constant, a number, times some value b, and this b value has the power of x. A times b to the x, a times b to the power of x. And we begin with taking a look at an exponential growth and an exponential decay function. How do I know it's growth? As this graph is going to the right, as x is getting bigger, f of x is going up. It is growth. Whereas in decay, as x is going to the right, as x is getting bigger, y is just getting closer and closer and closer to the x-axis, 0. So it's decaying. A couple things, we should look at their domains. If you recall, the domain is comprised of x, so it's all the values x. And if we look at where x is in the equation, b to the x, it's the exponent spot. If we take b and raise it to any power, you could raise it to the power of a negative number. In fact, any negative number, -1, -1,000, -10,000. Doesn't matter what the negative number is, you can raise b to any negative number. You can also raise it to the power of 0. It'll just equal 1. And you can raise it to any positive number, b to the first, b to the 100, keep going. So it can be any negative number, it can be 0, it can be any positive number. X can be anything. All real numbers, in fact. So the best way to state the domain is x is all real numbers. Or you could just shorthand that to x is big R with a bar through it. X is all real numbers. The range, however, is y, and when we look at f of x, it's y values. Notice that the y values, or the y-axis, is up and down movement. It looks like by these arrows it's going up forever, I agree, so we're going all the way up to positive infinity, any number way up there. But we're not going below the x-axis for some reason. Something is happening on the x-axis. The x-axis has an equation. The x-axis is the line y equals 0. It's the line where the height is 0, where f of x is 0. And notice the line seems to approach it, and if I keep going, it's just going to flatten out, and it'll never, ever go past the x-axis. In fact, it'll never touch the x-axis. So we say there is an asymptote, a line that we approach but never equal to, never touch. That's the x-axis or the line y equals 0. These two things mean the same thing. The x-axis has an equation. It's y equals 0. So we get closer and closer to 0, but we never touch it. That's the definition of an asymptote. A line, an imaginary line. Imaginary line that we approach. So get closer, closer, unbelievably close, so close to 0, but never touch, never equal to. Exponentials never equal 0. And if we never equal 0, we can never get underneath 0, so we can never be negative. We would say f of x, the range, is all the numbers above 0. And I'm not going to put an equal to line underneath because we can't equal this asymptote, 0. F of x is greater than the asymptote. Asymptote. Cool. And decay, luckily, is exactly the same. The only difference is the direction that we're increasing or whether or not we're decreasing. But no matter what, the domain, you can plug in any value for x in an exponent spot. Doesn't matter if it's positive, negative, or 0. The domain of any exponential is all real numbers. The range, well, they're still above the x-axis. Both of these graphs, exponential growth and decay, are above the x-axis. So it's all y values, all f of x values, greater than 0, but not equal to, because what's happening at the x-axis? There exists an asymptote at the line y equals 0, the x-axis, a line we approach but never touch. On day 2, we learned a brand new equation. F of t, or some amount, equals the initial value a times parentheses 1, sometimes plus, sometimes minus, some rate r to the power of time. This is just another version of an exponential in standard form. A is exactly the same. A, in both cases, will always be the initial value. B, however, B only gets used in specific examples when we are using words like double, or triple, or have. If I'm saying I'm taking some constant to some power, to the power of 1, to the power of 2, to the power of 3, I'm saying I'm doubling, or times 2, times 2, times 2, certain amount of times. Or tripling, times 3, times 3, times 3, a certain amount of times. Or having, times 1/2, times 1/2, times 1/2. We use B when we can describe our exponential growth or decay factor. What's the thing that we're multiplying over and over with when we're dealing with a factor? We use R as a rate, and rate as in a percentage, something out of 100. So we only use R if we're increasing, growing, or decaying, minusing, by some percentage. So we only use R, this formula, when we are given a percentage. Like, let's say you go to a restaurant or maybe not a restaurant. Let's say you invest in an account and you put $100 in the bank. And then every week after, or not every week, every year after, you get 100% of what you put in, plus maybe 15% return. So that would be 0.15. Whenever I say a percentage of growth, not double, not triple, not half, not these whole-looking numbers. When it's a percentage, we use R, the growth rate. So that's the difference between using B, a growth or decay factor, versus a growth or decay rate. And we'll see more of that later. Looking here, we have several growth factors. And notice factors because at no point do I see 1 plus or minus something. That has already occurred if I have something like 0.2 or if I have 1.2. Well, 1.2 is the growth factor. The growth rate is 1 plus the rate is 0.2. So see the difference there. Okay, now this is asking us whether or not it's growth or decay. No matter what, B, this growth factor, B, so we have some value, initial value A, and some growth factor B to the power of X. B will always tell us whether or not it's growing or decaying. Are we times 2, times 2, times 2, times 2, doubling, or times 3, times 3, times 3, times 3, tripling? These are growth B's. Whereas having, divide by 2, divide by 2, divide by 2, that is decaying. So we check and see whether or not our B value is greater than 1, then growth, or it's less than 1, decay. Now, B has to stay greater than 0, but as long as you know that it's not 0, it's some kind of number less than 1, then you could probably spot decay. The trick is, can you recognize your B value from the equation? If all equations exponential are of standard form A times b to the x. The trick is spot the thing that is attached to the x. X is attached to 0.2, 0.2 is the b value. And 0.2 is less than 1, so this is decay. Or 1.2 is our b value. A is 3, but b is 1.2. That's greater than 1. That is growth. And then we have something a little trickier, where are you sure this 2 is an a or a b value? Well, it's attached to x. That has to be b. The only question might be, well, where's a then? A is a hidden number written out front. If you don't have a value written, we assume it's multiplied by 1 out front. So this initial value is 1, its b value is 2. So we have a growth because 2 is greater than 1. In fact, it's doubling, times 2, times 2, times 2. I would use the word double here. Okay, next we truly have being able to tell the difference between a growth factor, like 0.94, and a growth rate, which is always a percentage. So let's begin with saying all of these are of the form a times, well, let's do this in red, a times some value b raised to the power of x. The initial value is a. That's easy to spot. It's 2. But the growth factor is not what they want here. They want the growth rate. So if I was going to state anything, this is the growth, well, it's decay because it's 0.94. B is 0.94. That's less than 1. It has to be decay. So this is the decay factor, 0.94, which makes decay. But it's not a growth rate. Growth rate comes from R. So B tells us whether it's growth or decay. R tells us the percentage. So let's think. How do we find the percentage that created the factor 0.94? Well, if you recall up here, the two equations are a times b to the x and a times 1 plus or minus r to the t. Well, we know in this problem it's decay because it's less than 1, so we better use minus. But b represents the totality of what happens after 1 subtracts r. So, I know b. B is 0.94. But I don't know r. So how do I find it? I know that if both equations are of the form, well, we have an a out front. Sometimes we have a b if we're doubling. Sometimes we write this as 100%. 1 represents 100% of the initial amount. And since we're decaying minus some percentage r. Depending on the situation, b is b, if we're given double, triple, or half, or it's a percentage, 1 minus some value r, but they represent the same object. So b could be said to equal 1 minus r. They're the same thing. Once you resolve 1 minus whatever this percentage is, you'll have b. We'll have 0.94. So the question is, what is the percentage that created it? If I end up with 0.94, 94%, then 100% minus something created 0.94. Well, 1 minus 0.06 created 0.94. And if it is a little difficult to see that 0.06, 1 minus 0.06 becomes 0.94, you could use your calculator. Or remember, 1 represents 100%. And R represents some percentage, some blank question mark percentage. So 100% minus some percent, and 0.94 is 94%. So if you think of it as 94% came from 100 minus something, it's got to be 6% or 0.06. So we're going to write this decay rate as we have decayed by 0.06, or you could call it its percentage, 6%. Depending on the question or the test multiple choice answers, they might want one or the other, so it's good to be able to go back and forth. So let's do that one more time with a growth. C is decay because B is 0.3. B is growth because it's 1.8. So let's say the growth factor comes from B, 1.8. The initial value, A, is 3. That's our y-intercept. And the growth or decay rate comes from if 1.8, which if I wrote this as a percentage, is 108%. You move the decimal place over 2 times if you want to go back to, sorry, not 108%, 180%. There we go. You move the decimal place over 2 times, so that's 1, move this over, the decimal place is now here, 180%. If B equals some 100% of the original value, and we're growing, so we're going to write plus some value R. Well, what's the percentage? 180% came from 100% plus what percent? And the answer has to be 80. So that percentage as a decimal is 0.8. In other words, 1 plus 0.8 is 1.8. So the percent rate, the growth rate, has to be plus 0.8 or 80%. Okay, every word problem that's going to be on your test or quiz is just, can you pick the right formula by parsing out, have they given me a growth factor, like doubling, tripling, or halving, or have they given me a percentage and picking the right equation? And then just knowing where to fill the right things in. So let's take a look at number 3. The foundation of your house has about 1,200 termites. The termites grow, well, there's a hint. I know this is a exponential growth. At a rate, well, there's the key word. They said the word rate, I better use R. This is the equation. Some initial value A times 100%, growth means plus, some value percentage R, raised to some time t. This is usually given as t. You could leave it as x, but most people plug in t for time. Almost all these problems have to do with time. So in our case, rate is 2.4%. There's our R. Let's convert that to a decimal. So take 2.4%, plug in your calculator and divide it by 100. That's what a percentage really is. Or take 2.4, and since we're dividing by 100, that's 2 zeros, we're going to take that decimal place and move it over to the left because we're dividing and move it 2 times. So the decimal place is right here. We have a placeholder 0. This percentage is 0.024 because we moved the decimal place over 2 times. Okay, so that's our R value. We might as well plug that in, 0.024, 2.4%. We have 1 plus this because it's growth. Let's see if we got anything else. How many termites will there be on day 30? Well, since this percentage, this rate is 2.4% per day, we're allowed to plug in 30 days pass. What's going to happen on day 30 to the power of 30? And then we have an initial value. I think they've given us. The foundation of the house has about 1,200 termites. How many will there be after 30? There's our initial value, 1,200 termites to begin with. Plug that in your calculator and you have an equation. But just remember, this is the growth rate. If you want to see what the growth factor is, the fact that we're growing is because 1 plus 0.024 is 1.024, a number that is greater than 1, so growth. Plug this in our calculator. Let's take a look. 1,200, let's see. Let's go to a calculator page. Let's see, start from scratch. 1,200, parentheses. I usually use parentheses because sometimes it's needed, sometimes it's not. It's better just to use it all the time if that's the case. So 1,200 times 1 plus 0.024 is 1.024, Raised to the power of 30 days. If I want to raise a power, notice what I just did. I plugged in 1.024 in the parentheses, but the cursor is not outside. I need it outside, so I'm going to click right once. And now I can raise this whole parentheses to the power of something. That button is this housetop looking key. It's called the caret key. When you hit that, a little box opens up that lets us fill in the exponent. I'm going to type in 30 for 30 days. Hit enter, and we have our answer. So we went from 1,200 termites, and we've more than doubled to 2,444.44. If you're ever curious if that decimal keeps going, click up to highlight it, hit enter. Oh, yep, that decimal just keeps going. It's not a repeating number, it just keeps going. I think we're going to round that because they started with 1,200 termites. We should probably end the problem with a whole number if they gave us a whole number. So I'm going to round 2,444.44 termites, and because 4 is less than 5, I'm just going to round this to 2,444. Round down. So all these problems after number 3 are nothing more than percentage problems. So we should use the formula for every single one of them, 4, 5, and 6, a times some value 1 or 100%, sometimes plus, sometimes minus, depending on growth or decay, some value r, a rate to some power t. So 4, 5, and 6 are all percentages. They should all use r. But then we get to 7. Tobias ate half a banana in his room and forgot to throw the rest away. That night, 2 gnats came to visit the banana. Each night after, there were 4 times. 4 times as many gnats hanging around the banana. That's telling me that we're looking at not a percentage, we're looking at a growth factor. Times 4, times 4, times 4. This represents times 4, times 4, times 4, over and over, depending on the number of nights. So write a function that models the gnat's growth. Tobias ate half a banana in his room and forgot to throw the rest away. 2 gnats came to visit. So we're starting to begin with 2 gnats. That's our a value. Oh, we are using a times b to the power of x. So that's a b value, not an r value. 4 times is representative of times 4, times 4, times 4, over and over again for every night. So we have an initial value, 2 gnats. Every night we have 4 times as many, and it happens every night. So let's replace x with t for time, every night. And since it's a function of time, let's say gnats per day. So we can make this a function gnats. Let's use the letter capital G for gnats. G of t, where t is the amount of time in nights that pass. Okay, how many gnats will be swarming around the banana at the end of 2 weeks? Well, remember, this function is in terms of nights pass, not weeks. We can't just plug in 2. So how many nights are in a week? Well, there's 7 days in a week, so there should be 7 nights in a week. And there's 2 weeks, so 14 nights. 14 nights pass. How many gnats should there be? We started with 2. Every night it's times 4, and it's going to go on for 2 weeks. 2 weeks, that's 7 days, 7 nights each week. That's 14 nights. So to the power of 14. And now we have, this should all equal, let's see, 2, gotta plug in my calculator real fast, 2 times 4 to the power of 14, and I'm getting about 5, 3, 6, 8, 7, let's see if this is rounding, nope, it's not, it's a whole number, 5, 3, 6, 8, 7, 0, 9, 1, 2, so 870,912 gnats. So you started with 2 gnats. Better clean up that banana before we're swarming with gnats. Okay, jumping to one of these graphing problems, starting from scratch. we're given an exponential. Remember, you have a calculator, so you are allowed to plug this in your calculator. Just remember, if it's given to you with a parentheses, it's probably recommend you use a parentheses. So this is 4 times parentheses our b value. Go ahead and type that in if that's what you'd like to do. But we could also do this by hand. First, we know that all exponential equations are of the form y equals a times some growth factor or decay factor b to the power of x. And we have a. So a is the initial value, 4. We know the y-intercept is 4. You automatically know where the y-intercept is because that is the a value. 1, 2, 3, 4. Right there. Next, domain and range will always be the same for both of these. So the domain of both exponentials, growth, decay, percentage, not a percentage, domain is all real numbers unless stated otherwise, like they put a hole or they put a dot. The range, again, will always be above the asymptote. In this case, the asymptote will always be the x-axis, y equals 0. That will never change in this class. F of x has to be greater than, strictly greater than 0, and not equal to. Do not put an equal to, because we can't equal the asymptote. So this 0 represents the asymptote, a line we approach but never touch. Next, if we really do want to graph these or be able to recognize the answer choice of a graph easily, we have to tell whether it's growth or decay. In our case, the b value is 1/4. That is decay. Less than 1 decay. So what does the 1/4 really represent? 1/4 to the power of 1, to the power of 2, to the power of 3. It's 1/4 times 1/4 times 1/4 in any amount of times. So we say 1 day passes and we're at x equals 1. And I want to know what happens at x equals 1. What's the y value here? Well, we started at 4. Multiply 4 times 1/4, or in other words, 4 divided by 4 is 1. Start with 4 apples. Divided by 4, we have 1 apple. Divide 1 by 4, we're now at 1/4. So after 2 days, 1/4, and then 1/8, and then 1/16, smaller and smaller and smaller. And if we want to know what's happening to this side, well, we're going to grow. We know it's going to grow, but to be exact, we're going to grow by the opposite of 1/4. If in the future we divide by 4, in the past we multiply by 4. So if I go 1 day in the past to -1, then I'm at 4. Start with 4 at day 0. Go 1 day in the past. 4 times 4 would have us at 8. So 4, 5, 6, 7, 8. And then times that by 4, and we should have 32, but I don't think that'll fit on our graph. So this graph just grows in the negative direction. And then as we go in the future, we get closer and closer and closer and closer to 0, the asymptote, because if we go from 4, divide by 4, 1, divide by 4, 1/4, divide by 4, 1/8, 1/16, 1/32, we're just getting smaller and smaller and smaller, closer to the asymptote, y equals 0, but we never touch it and we never equal it. We can never equal 0, the asymptote. Similarly, if we want to do it this way, our a value is 2. That's our y-intercept. We plot 2. The rule is 3. The growth factor is growth because times 3 is bigger than 1. We start with 2, go 1 day further. 2 times 3 is 6. 6 times 3 is 18. If I want to go into the past, 2 divided by 3 is 2/3. Divide that by 3, some amount, divide that by 3, divide that by 3. We're getting smaller and smaller and smaller, but never quite 0. So we have the basics of how to graph an exponential function. Next, you'll be given a chance to tell the difference between several equations lined up and tell me which ones are actually exponential. Exponential equations have to have x in the exponent spot. X has to be the exponent. If it's not, then it's not exponential. So look at 3x squared. The exponent is 2. It's not x. This is not exponential. Y equals 3 times 2 to the x, it's clearly exponential. This is a times b to the x. X is the exponent. This is, yes, exponential. 5 times 1/2 to the x. X is the exponent. Yes, this is exponential. 3 plus x squared. Once more, the exponent is 2. That is not exponential. Okay, we finally hit the section of the review where it's spiral review. This is review from last unit, units before, units from the first semester. So this has nothing to do with exponential. Do not think exponential. In fact, look, negative 16t squared. X is not the exponent. This is not exponential. It's quadratic. Jason jumped off of a cliff into the ocean, so automatically I know he's on a cliff. He's jumping, this person, Jason, is jumping off, going into the ocean. That's a quadratic graph. What goes up must come down. So he starts at a certain height, we don't know what it is, or do we? Yes, we do, because this equation that we were given is of the form a x squared plus bx plus c, and c represents the y-intercept. This person, Jason, is starting at a height of 480 feet. So this is the y-axis. So that must mean our x-axis is time, t for time. So starting at 0 seconds, Jason jumps off the cliff. How much time passes before he hits the water, probably? Or let's see what they're asking. He's vacationing, blah, blah, blah. He starts at 480 feet on the cliffside, where t is time in seconds and h is his height in feet. Well, it makes sense that the ocean is 0 feet, so do not don't count anything below the ocean floor, like -2, -3. Let's keep it above 0. This is the ocean. And how long did it take for Jason to reach his maximum height? His maximum height would happen at the vertex of the graph. And we need this coordinate. So the maximum would happen at the highest point of this graph, the highest height. What they're asking is when, how long. So we need the time, we need x. In other words, we need the axis of symmetry. We need to know at what time is this graph in the middle. So we plug this whole thing into the calculator. Negative 16x squared plus 16x plus 480. So open up a fresh graphing page. And we're going to type in negative 16x squared. I believe it was plus 16x. Yes. Plus 16x plus 480. This will not appear on the graph because 480 is a massive number and it won't show up. We see the negative side. Well, remember, we're not using negative time. The x-axis is time, so do not use this 0. This is where he landed. That's the ocean floor. That's when he landed. So just counting, I think I could see 1, 2, 3, 4, 5, 6 seconds maybe. But if I'm not sure, we should use the tools. Menu, trace, graph trace. And the nice thing about graph trace is the first point that ever pops up is the y-intercept, and we don't even have to change the window. It changes it for us. So that's not what we need. We know the kid starts at 480 feet. The maximum that pops up is 0.5, 484. So his maximum height, well, he can jump 4 feet high. Good for him. Gets 4 feet higher, and then it takes him 0.5 seconds to get to that highest point. So at 0.5 seconds, Jason reaches his maximum height. Half a second. What was the maximum height of Jason's jump? 484 feet. Jason hit the water after how many seconds? Well, now we need to find this x-intercept, this 0. We need to know, when did he hit the ocean? When did he hit the x-axis? So we go back. Let's just click. I'm sure we'll jump there pretty quickly. Hopefully. Oh yeah, he's falling fast. When are we going to get to x or y equals 0? Oh, passed it. There it is. 6, 0. I was right. 6, 0. He hits the ocean water. That is time 6 seconds, 0 feet in height. That is the ocean. This is the time. It took him 6 seconds to hit the ocean floor. The rest of the problems that are on this page, 11, 12, 13, they're all quadratic. negative 16 squared, negative 16 squared, negative 16 squared. They're all quadratic, which means if they're real world, it's probably something launching off or something falling down. Graph it in your calculator, find the picture, and answer these questions. Remember, the x-axis is almost always time, and the y-axis is almost always height when we're dealing with projectiles, when we're dealing with parabolas. Do not use the negative versions of these graphs. So they probably start at some height, they probably hit at some time. Only use the positive axes. Now, you probably don't have a calculator at home, but if you don't, that's okay. I say practice in class, and I'll be watching you guys. Use the time wisely in class with the calculators. The next section can easily be done at home. We have a bunch of linear equations. So how do I know it's linear? There is no exponent on x. X is not itself the exponent, and there's no x squared. So this is a linear equation. These are straight lines. Sometimes inequalities, sometimes equal signs. But in essence, can you get everything to one side and solve? The only thing to keep in mind with inequalities is when do inequalities, either less than, equal to, greater than, less than or greater than, equal to, when do these things switch directions? And at any point, you divide or multiply both sides of the equation by a negative. It's the only thing to keep in mind. If at any point you do that, you have to switch directions of the inequality. And maybe we'll see that here. So let's begin with super basics. My suggestion is to get everything to one side is continue to go with PEMDAS. Combine all your like terms. Now, what do I mean by that? This left side of the inequality has an x and an x and an 8 and a couple numbers. There's a parentheses. Let's resolve this side so it's all simplified. And this side, I have a negative 10 plus x. These aren't like, so they can't combine. This side will just be left alone for now. But let's fix the left side. I have a negative 6x, nothing to do there, minus a parentheses. Recall, if there's nothing written here, this negative is a negative 1 times that parentheses. We have to distribute that negative to both of these. So positive 2x in the parentheses becomes negative 2x. Negative 8 times negative 1 becomes positive 8. This is distributing the negative. And we bring everything else down. That was the only thing that needs to be done. I have negative 6 here. I have greater than or equal to, I have negative 10, and I have a plus x. Bring everything else down. All we did was the negative 2x plus 8. Next, combine like terms. Again, the right side has no like terms, but the left side does. I have negative 6x minus 2x. The only thing for them to be like is they have to have the same variable, the same letter x, and they have to have the same exponent, which they do. It's not written, but they're both raised to the power of 1 if it's not shown. Same x, same exponent, they are like. So negative 6x minus 2x becomes negative 8x. I have negative 8x's now. Plus 8 is greater than or equal to negative 10 plus x. Once you have combined all like terms on both sides of the equations, now you get x to one side. So we choose. If I want to get negative 8x to the other side of the equation, I would do the opposite of its sign. Add 8x to the other side. When things travel across the equation, they change signs. So that would be x plus 8x. That's kind of nice. That'd be positive. Or if I wanted to take x and send it to this side, which you can, I would minus x, and I would have negative 9x. Also fine. Just decide, which side do you want x on? The left side or the right side? Let's say I want to demonstrate for you guys the switching directions. So I'm going to send x to the other side of the equation by subtracting it. That way, at some point, I am going to have to divide by a negative, and I'll show you what happens to the inequality. So now I have negative 9x plus 8 is greater than or equal to negative 10. Okay, everything with an x is on the left side. This 8 does not belong. I need it over to the other side, subtract it, minus 8, and I have negative 9x is greater than or equal to negative 10 minus 8 is negative 18. Okay, I need to shrink this just a bit. At that point, I'm about to, we've combined all the x's. There's only negative 9x on this side, and there's constants on this side. No more adding or subtracting. The last step you should be taking care of is this negative 9 is attached to the x by multiplication. If I want negative 9 gone, do the opposite of multiplying by negative 9, which is dividing by negative 9. And now we must follow this rule. The inequality switches directions when you divide or multiply both sides by a negative. I just did. I divide both sides by negative 9. Immediately, I'm going to switch that inequality from facing open mouth to the left to facing open mouth to the right. And now I have negative 9 divided by negative 9 is 1. It's gone. X is less than. Negative divided by negative is positive. 18 divided by 9 is 2, so positive 2. X is less than or equal to positive 2. The rest of these problems are very much the same, so I'm going to take a look at number 17. What do you do when you got a parentheses inside of, these are called brackets, but they're really treated like parentheses as well, just so that you could tell the difference between them. So a parentheses inside of a parentheses work from the inside out. So we have a 4p plus 5 on the inside of the biggest parentheses. We should do this first. I can't add p plus 5. They're not like. But I can distribute this negative 4 to both p and 5. I have negative 4p. Negative 4 times positive 5 is negative 20. Okay, these large brackets are still here. And so is the 2p and the minus. Oops, sorry, not the minus, because we distribute that minus. 2p minus 4p equals 25. And there's still a 5 out front. Okay, now I have a large parentheses. We should combine anything we can on the inside. 2p minus 4p is negative 2p minus 20. Bring everything else down. And finally, this parentheses cannot be combined any further. Negative 2p and negative 20 are not like. Leave them separate. Distribute the 5 on the outside of the parentheses, and the parentheses will be resolved. 5 times negative 2 is negative 10p. 5 times negative 20 is negative 100, equals 25. Okay, last step, just like the other problems, once you have done all the parentheses, combined all the like terms on both sides, 25 is just 25. Negative 10p and 100 can't combine. Everything on each side is combined completely. Get all the variables to one side. So I have a p. Let's say I leave the p on this side. I want to take this 100 to the other, so plus 100 to both sides. And now I have negative 10p equals 25 plus 100 is 125. Okay, only p on the left side and only constants on the right side. Get rid of the coefficient of the variable. So negative 10 is being multiplied by p. Get rid of it by dividing by negative 10. And now we have, oh, we just divide both sides by a negative, but there's nothing to flip-flop because that's an equal sign. Equal signs do not switch directions. And now we have p equals positive number divided by negative number is negative, and 125 divided by 10, it's just going to move the decimal place over once. So this is 12 and a half.